Okay, now we can start with this session. We go to Lambda functions and const expert keyword to finish the, let's say, the overview, the major features of C++, 11, 14, and some 17. So we have also already seen some of the lambdas in my slides, also in Nora's slide. And lambdas are actually useful, for instance, to make your code look nicer, in the sense you can understand, you can read the code in line often instead of having to look for where a function or a function object is defined. So you can read the code there. And there are quite useful abstractions to use. So lambda takes its name from the concept of lambda calculus. It's basically which was developed in the 1930s and then became the foundation of the functional languages. The idea is to be able to create a function on the fly. You create a function with no name, and you can use it. So it has a special function, a special syntax, sorry, and it basically has the square parentheses as here, a list of arguments and body. As everything else in C++, this has type, which is encoded into this auto here. So we can create a variable f, which is basically a function. It has a type. The type is implementation specific. Basically, you can inspect the type. You can know what the type is, but it's up to the compiler to generate a type for you. So this lambda will have a type, but it's not going to be very useful for you, but it will have a type. When you create the lambda, you don't call the lambda. So you just create it, and you can call it as you would call a function. So for instance, if I call f with 45 and 77, and I get the result back, which is x, right? I create my lambda, I use my lambda. The interesting part, for instance, is that you can use these lambdas inside std algorithms. So I can do for each vector element. So for vector begin to vector end, you apply this function. You increment every element in this vector, right? This is a lambda. This is empty square brackets for now. And we'll have we'll take a reference to an int, and we'll take that value int and we'll increment by 1. And this vector is a 1, 2, 3, 4, 5. So the output after this algorithm is being executed, the vector will contain 2, 3, 4, 5, 6. And the advantage is that, so before lambdas, you should have put here like a function object or a function pointer or something, whatever, but it's not going to be defined there. You just see the function you have to call. I mean, for instance, you get a function object, instantiation, a function object itself, and then where the operation is defined is where that thing has been defined, maybe in a header or above. So in this case, you can see the code straight up here. So what is the mental model that you can use to understand lambdas? For me, at least, when I see auto f equals empty square bracket, 2 arguments, and this body is like I'm constructing an object. I'm of a given type, and the type is a struct with some name, which is decided by the compiler, and has the operator function call, which takes 2 parameters, A and B. It is const, so it's not allowed to change the state of the object, and then it returns A plus B. And you can see the arguments are the same you pass to the lambda, and the body is the body of your lambda. This might be the mental model you might want to use to understand what lambdas do. And the name is not up to you. The name will be picked up by the compiler. So now we can put stuff inside those empty square brackets, and you can use this square bracket to capture values. Capturing is a mechanism to give access to your lambda to, for instance, local variable which are in your scope. In this case, you have an integer t8, and you capture t. So now inside your lambda, you have access to t. And for instance, now the lambda does t times a plus b. And when you call x f45.7, then it will be 45 plus 7 times 8. The mental model is that is like you have your object which has an initialized, which has a data member which is initialized to 8. And this capture is to show you that this capture happened by copy. You take the value of t, you copy it, you keep the same name, but they're basically not the same object. So if I change t after the lambda here, the inside you still see t equal 8. So I'm capturing the value of t at the time of the instantiation of this thing. As you can see, it's still const, and this is the value. I'm taking the data member t, and I'm using inside my function. And this is what the capture basically does. Now the problem is that this t inside here is an immutable object. As you see, this is a const member function of this class. So if I change t, I will get a compile error, because that member function is const, so it's not allowed to change the state of my function object. So in order to be able to do this, I can put the keyword mutable in my lambda, and so I can change the value of t. The equivalent mental model is that when I capture t, I put the mutable keyword in front of my data member. So even though it's const, I can still do the change. But still again, if I change t inside my lambda, I'm not changing the value of t. I'm capturing the value of t, which is 8. I'm putting it into my function object. I can change t, but I change the t, which is a data member. So after this computation happens, t is still equal 8. I don't know if you knew about this keyword, mutable. You can put in any struct. It's not something you are encouraged to do because it kind of breaks the abstraction, the encapsulation. If I'm saying a member is const, I wish that it is const. That's not changing the state, but you can override that behavior with using that keyword. In C++ 14, as you have seen here, the type of the arguments is given here, right? It's an integer and an integer. And soon after this was approved, the idea that came to people say, why can I not have a template lambda? Because it's C++. You want to complicate things. And so instead of doing template, instead of using the template keywords, they say, well, we can simply deduce the types at the moment of the call. So we use auto A and auto B, and then return A plus B. And then we can do this, and it will be 45 plus 4.67, which is a double. And the mental model you have is that instead of earlier on that you have the operator with the list of arguments, now the operator takes the argument as template argument. So your operator is actually a template member function, and will be instantiated for every lambda call. So at this point, it's just putting the template here. So you generate that member function whenever you need it. By the compiler, of course. It's not runtime. So the auto keywords become templates arguments. Also on C++ 14, you can rename variables. So I can say, I have a Boolean I call sum, and I want to use a different name inside my lambda, so I can always say flag is equal sum. And this behave like something like you have a data member flag, and you have a constructor for your lambda that takes a Boolean and instantiate flag with that Boolean there. And then if flag is true, to do A plus B, otherwise A minus B, the body doesn't change. So the problem might be that you might want to have side effects on your lambda. So you want to capture a variable, but you want to capture by reference. And in this case, you can do it. You can capture sum by value, and x you won't capture by reference. You get your two arguments, and then x is equal something, and then you return something from your lambda. And then after you have done this, the value of x is modified. Of course, if you take a reference to something, you need to be sure that when you call the lambda, that reference is still active, is still valid. But you can capture. And the mental model follows, basically. Many times, you will just capture everything. Yep. You take the mic, please.
So in the previous example, could you have returned x?
Yes.
Okay.
It will be copied into a value, right? I think. Many times you might be a little bit lazy, say let me capture everything by reference. And you can do it by putting an ampersand inside the square bracket. And basically it's equivalent to the compiler doing searching for all your scope variables and capture every variable, or if you want, the compiler can go inside your Lambda and capture everything that is not defined inside Lambda. But for instance, I capture everything by reference, and then when I change sum and I change x, then I will see the effects outside. So every change I make inside my Lambda will be visible outside, and basically it's like having all data members to be references. And the thing follows. Yeah, this is actually wrong code. It's not correct. It should be bool ref and int ref to do the capture correctly. But on the other hand, I might also be willing to capture everything by value. Just give me a copy of everything, and you do it by value. So you put an equal sign inside the square brackets, and then you have access to all the variables that are available in your scope by value. You can also capture everything, but you want something special. For instance, you want to capture everything by value, but X I want to capture by reference. Yeah?
On the previous slide.
The mic? Sorry.
Why do you have the mutable keyword this time in your mental model? Because everything is...
Because I'm actually changing the values here. So again, as before, I'm capturing by value. So if I change my values in here, it will be a compiler header because my operator is const. So I put in the mutable keyword, allow me to change the values.
The change won't be reflected back to the
It's not reflected back to the main scope. Yeah, good catch. I didn't see that. So you can capture everything except something, and it might be that you want to control also the return type that you want to yield from your Lambda, because maybe the computation will cast the type as something. If I pass an integer and a double, and I do the sum, I will end up with a double. And maybe I want an int as a return value. So I can specify with the arrow, I can specify what the return value is for this function, or I can say whatever it's return by reference. Right? So I can force this behavior here. Lambdas has a nice feature that can be automatically converted to function pointers. So if I have an old C library that takes function pointers like this, it takes a function pointer to a function that takes two integer and return an integer, then I can pass to the run a Lambda directly. And this will be converted to a function pointer, and then it can be called directly from the function. And here I can actually check that the function pointer is not null. If it's not null, then I can call the function, and the function returns the sum. You might put lambdas inside member functions. You may actually return lambdas from member functions. And in this case, what happens is a little bit less clear. I have a lambda, I have my class A with a data member A, and then I have a lambda which captures everything by value, and inside I define another variable A, and say A0 to A++, and then I output A. And then I call my lambda. Lambda with no argument, so I can put the lambda there. And interesting, this does exactly what you want. It prints 1. But if I don't define my own thing inside here, this will actually work because it will capture by value the current scope. But this A++ is going to work. So what happens here is that capturing with equal will capture this pointer by value. And so now I have access to this one, which is actually this data member, which is something you might want to do if that's what you want to do. But A is available. It's available without accessing through this pointer. It's actually available there. Yeah.
So for his previous remark about the mutable, in this case, so when we do by copy...
This doesn't need to be mutable.
Okay, because it's by copy.
Because it is this pointer which is copied, you're not changing this pointer, but you're changing the value pointed by this pointer, which is A++. So it's like, which is A. So you're not changing the pointer, you're changing the value pointed to, and there you can do it. So it's really a different behavior if you want. I mean, it's the same behavior, but there is kind of shortcut here, right? It's the fact that you don't see this pointer. This A is actually this A because I'm capturing this. So this is equivalent to doing this A++. And while this is not changed, because this is a pointer, I'm not changing the value of the pointer, I'm changing the value pointed to, and that this will actually do the change, will increase A++. So these two alternate and alternate 2 are actually equivalent. So in this case, if I define a variable A inside the scope of this function, and I'm capturing everything by value, then I have access, A will access this guy, and then I can access these A to explicitly address A. So by default, you capture the scope, so you will capture this guy first, but you capture this too. So if you want to access the data member of the class, you have to explicitly capture, say, this arrow A. And as before, this doesn't have a side effect. So if I change the value of A after this is still 5. Because I'm not capturing by reference the variable in my scope. So here we say that A is actually shadowing the data member. So you are defining a new one inside. This is the data member of A, because this is captured by value. And this A will shadow the data member A. In C++ 17, they realized that this capture of this is a little bit confusing. You're capturing a pointer by value, and they didn't like the idea. Why can I simply copy the whole class if I need it, right? Instead of copying just the pointer, I want to copy the whole object. So if you do if you capture this, then you will make a copy of A, a copy of your object and pass it inside. And there this A++ will not affect the original A++, but only the copy. This was driven actually by an HPC use case. There were people at Sandia National Lab that were trying to port an old physics code, was particle physics code, and they wanted to port it to C++, and they wanted to use the Cocos library to run this application. And so Cocos is a high level, well, not so high level, but it's an abstraction in C++ that helps you defining parallel computations. And they basically transformed all the old Fortran code first into member functions of these big objects, and then they wanted to return the lambdas from these classes and then schedule these lambdas as tasks in their execution model in Cocos, and they realized that they were not copying the objects, they were like really changing the original objects, and they had to do special work basically to make that work for their test case, because they didn't want to just capture this pointer, they wanted to just copy the whole object in. And this is, this change was actually triggered by that use case. And this is idiomatic, right? You need, if you say star this means copy this object inside my lambda. And of course, the class must be copy constructible. If you don't have the copy constructor, this will not work. So nothing esoteric really happening here. Your class needs to be able to be copied, otherwise the copy cannot happen. There is another, so lambdas are very useful, and they don't cost much. Actually, it's like really, they don't introduce any runtime overhead other than the construction of the lambdas, of these function objects. So it's not a big deal, but there are cases in which they are not enough, or cases in which you have to do something else. So suppose that I have now a function foo that takes two integers and returns a float, but also I have a function object which is an object of type A, which can be called as an integer as a function. So you have the operator and the operator parentheses with two arguments, and then returning the float. What you can do is you can use the standard function, stud function. Stud function is a wrapper around the concept of a function. So you can say this std function of a function that takes two integers and return a float. This is the signature of my function. And I can say, well, f is going to be a lambda, and a lambda that takes two integers and return the static cast of to float of a plus b. Then you can call f with 3 and 4. Then in the same code, you can say, well, you know what, foo, I want now f to not just be this lambda. I want f to be equal to foo. And then I can call f with 3 and 4, and it will do the trick. It will call foo with 3 and 4. Or I can say f is just my function object. And then you call f with 3 and 4. Very powerful abstraction, very useful sometimes, depending on what you have to do. When you reassign a function to a stud function, you call it retargeting. And you can actually retarget into member functions to the operator parentheses of an object. But the cost of this is that when you call this, it is going to pay a virtual function call. You familiar with virtual functions? So when you define a base class, which has the virtual function, you can redefine that function in a derived class. And when you call the derived method function, it will look up, well, if you call the base function, if you call the base class member function, it will automatically go to the proper derived class implementation, right? So I have a base class with a function, I have the derived class with a function. I pass the base function pointer, so the base class pointers, and I can call the derived function. But this has a cost, and has a cost of basically some lookup. The implementation trick that I usually do is to put something which is called the vtable, the virtual table, before your class, where you get the pointers to the actual functions that you want to call. And this takes some time. So there are some overhead in using stud function. Instead of using directly the function call, directly the lambda, or directly the operator for your function object. So you don't want to do this in your innermost loop, usually, unless you're doing something very runtime specific, like you're doing a compiler, or you are implementing a compiler or something like this. So you need to have this flexibility because you don't know what will happen at runtime. But if you know that at runtime, you know what function to call, you should always try to call it. There's also another feature which is called binding. You shouldn't really use bind unless you really have to. But the idea is that you can reshape a function. If I have a function that takes 2 arguments, and I want to rewrite it to, let's say, reshape that function, for instance. I want to get the function that is basically foo, but in which the first argument is really what I care, because I know the second one is always going to be 4, right? So I know I'm going to call foo all the time, but I'm going to call foo where b is always 4. And then I don't want to write 4. I want to just call the new function that substitute this. And you can do it with a standard facility, but you need a little bit of features. One is the placeholders. So you can do using namespace std placeholders that gives you access to this _1, _2, _3, _4, _5. Underscore is just to make sure that that number is actually a symbol which is valid in C++. You cannot have a variable name 1 or a type name 7. It has to be underscore. Underscore 7 is a valid identifier. And now you might say, I want to bind the foo where the first argument is just a placeholder and the second one is 4. So now when I call, and I want to call this new function that I have, x, and when I call x of 7, it is going to be foo with 7 and 4. Yeah. Microphone?
Would it be better to use a lambda function instead of bind, or?
Yeah.
Okay.
No. Okay, it depends what you are doing, right? You should, let's say, bind as a drawback that we will see later on. And go ahead.
So basically, after C++14, there is no reason to use bind at all.
Yeah, you can always avoid that.
But for C++11, there are use cases where you want to. So, and it's quite subtle, but bind can bind works with so-called generic functions, and you cannot do. Sometimes you cannot do. You cannot substitute lambda bind by lambda because you need generic for that. But those cases are really rare.
Yeah, especially with generic lambdas, when you can generate the stuff that you need, probably. Yeah, I mean, there are other ways of doing it. I'm just showing because this is something that, you know, it's interesting that you can do things like this. I like the fact that you can define the interfaces to modify the existing state of your code. Let's say you can look at your code, you can transform basically how you look at the code and give to and really give to your user, for instance, different interfaces, or you can play with a lot of stuff. And just show you a couple of examples. So there you can use bind. Also, you can use it in a very strange ways. Like the first one is the one that we saw. The first one is a placeholder, and the second is for. But then I can use both twice the same placeholder, and then this placeholder, it means that there is one placeholder, so you need to pass one argument, and the result of this function is always 0, right? Because it's 6 minus 6, and I can call it without argument, with just one argument. If I'm using just the second placeholder, I need to pass 2 arguments, but only the second one is actually picked up, so the result is still 0. Or I can do -2, -1, so I can actually swap the order of these arguments. So placeholder 1 will be 6, and placeholder 2 will be 4, but then I'm passing 2 as first argument and 1 as a second one, so I will get -2 instead of 2, right? Because I'm swapping the arguments. Yep. Maybe what is the microphone?
Does standard bind propagate no except qualifications on the thing that it's bounding?
I think so. I don't know. I need to look it up. Do you know, Anton? Unlikely. Okay.
So unlikely because it was basically designed before no except.
Okay. Yeah. The no except is later. Go and find out. The same problem with the standard threads is the fact that when I say for here, even if I say x or y, whatever variable, this is by copy. So if I want to pass a value by reference, I need to say so. So if I have this variable x and y, now my bar function takes integers int a and int b by reference for some reason and does this computation. And now I can bind bar, and then to the first placeholder is okay. You pass it through. It will be passed as a reference, okay. But if I want to pass x here as the second argument, and I want that to be passed by reference, or it has to be passed by reference because otherwise this will actually complain because it has to be a reference, then you can use stdrefx. This is another case in which stdref can be used or should be used. And then if it is a const ref, you have a stdcref. This is also another standard facility you can use to specify I want to give this value as const reference. I encourage you to go and see how this ref and cref are implemented in the standard libraries. It's interesting. Okay, so now suppose we have still our run method, and then we want to accept a function pointer or a function that takes an integer, two integers, and returns an integer. And we can run directly with the lambda, but we cannot run with the bind. So the bind has this limitation that cannot be converted to a function pointer. So this will not work. So if you try, you get compile error, and there's nothing you can do about it. But you can do std function. You can have the foo, and then you can run myf, and myf is a stud function, and then you can retarget your function to actually be a function pointer of a certain type. So you can take a stud function and make it look like something else. But if you retarget in the wrong way, so if I retarget my f with an integer, a function that turns an integer and takes a float by reference, this guy will become just a null pointer. Things you can do. Sorry, couldn't run this one. Why? My f cannot be run. Oh, yeah, sorry, yeah. Stud function cannot be converted to a function pointer. So stud function by itself cannot be converted to a function pointer, but you can do it with this target thing. You can get this function pointer out. And if you get the wrong type, it will barf you. With member functions, well, that's I like this example because it shows what the member functions really are. So I can take a stud function of a function that takes two integers and returns an integer as a member function of A. So A is a class, it has a static member, static int member, and I can say, just take that function. A static member of a class is just a function that does not access the data members of that function, right? It can only access, it cannot access V. You cannot go into the static member and access V. The reason is that this static member is not going to to take this pointer as an argument. It will just be a regular function that takes 2 arguments and returns an integer, and is just the name of this function will be a : member or whatever the compiler mangles it. Right? So, and this is a static function, the static member function of that class. And now I can take the member 1, I retarget to this function, and I can call it. And now I want to actually I want the standard function to this member, which is not a static member function. It's a member function that takes 2 integers and return the data member of this class. Now the problem is that this function is not just a function that takes 2 arguments. It's a function that takes 3 arguments. 1 argument is this pointer. So what you have to do to capture this is stud function of a function that returns int, takes a pointer to a and 2 integers. You call it member 2, and you get the address of a : member 2. And this is the syntax you need to use. And now you can call member 2, and you pass the address of a. A is this class here, and with the 2 arguments. And you can call that member function. And I like this example because it shows how this thing is implemented behind the scene, right? It's nothing magic. It's the thing that basically what a class does, it prevents you from being able to do things. You basically think as those functions are part of the object, but they actually be compiled as functions with a certain signature and a certain name somewhere in your executable. And then what you can also do, you can a stud function of a same function that ints an int and takes an int. And now I bind my member 2, so this non-static member function, and I can bind the first argument to be the address of a, and with the placeholders 1 and 2, and now I can call this function as it was a regular function. Because the object has already been bound, right? I will call the member function of that particular object. Best practices, lambdas are usually good. You can use them. Bind is as efficient as calling functions. It's really efficient, but there's a lot of problems, and you can write code without bind at all, and it will be as efficient. So bind is efficient. You cannot retarget it to become a function pointer, and so you cannot interface with C libraries, for instance, that takes function pointers. And stud functions are actually have some runtime overhead, so you should use them with care, especially if it is in the innermost loop of your scientific simulation. Questions?